I've been thinking about a recent paper I came across that addresses a significant challenge in getting self-driving cars ready for widespread use, specifically how these vehicles see the road. We're at a point where autonomous systems are starting to shift from relying on expensive sensors like LIDAR to primarily using cameras, much like human vision. While cameras are more cost-effective and could make self-driving technology more accessible, this shift presents some interesting technical hurdles. The paper dives into these challenges and introduces a framework that might be the key to overcoming them, making the future of autonomous driving more feasible. What stood out to me in the paper was how the authors highlighted the difficulty of transferring a self-driving system from one vehicle to another. Even slight differences in camera setups, like how they're mounted or the type of lenses used, can cause major issues. For example, a system trained on a Tesla might struggle to adapt when placed in a Honda due to variations in camera positioning. The paper explains that this isn't just a matter of teaching the system to recognize objects, but also ensuring it can adapt to different eyes or camera configurations to perceive the world accurately. The paper introduces a concept called extrinsics and intrinsics. Extrinsics refer to the camera's position and orientation in the world, while intrinsics deal with the internal properties of the camera, like lens type and field of view. Both are crucial for enabling a self-driving car to accurately judge not just what objects are in its surroundings, but also how far away they are. The paper emphasizes that these small differences between camera setups could lead to errors, like mistaking a fire hydrant for a pedestrian, which is a real-world problem the system needs to handle flawlessly. What's really exciting about the paper is the proposed solution, UniDrive. UniDrive essentially acts as a universal translator for different camera setups, creating a standardized virtual camera space. Instead of needing to train a self-driving system for each specific vehicle model, UniDrive enables the system to interpret camera feeds from any setup by translating them into a consistent format. This makes the technology much more flexible and scalable. UniDrive uses a method called ground-aware projection, which was particularly fascinating to me. It doesn't just assume the road is flat like some systems do. Instead, it factors in things like the Earth's curvature, allowing the system to account for different camera heights and vehicle types, like SUVs versus sedans. This ensures that the system can accurately measure depth and distance, regardless of the vehicle it's operating in, which is key to avoiding errors in real-world driving. The researchers tested UniDrive using a simulation platform called Carla, and the results were promising. UniDrive consistently outperformed other state-of-the-art models, even when faced with significant variations in camera setups. The paper discusses how UniDrive had a much smaller performance drop when switching between different configurations, which suggests that it's a more robust solution for adapting to multiple vehicle types. While the paper presents UniDrive as a major breakthrough, it also acknowledges that there's still a long way to go. The next step is real-world testing to see how UniDrive performs outside of simulations, where unpredictable factors like weather or other drivers come into play. But if the technology can scale beyond the lab, it could have a huge impact not just on self-driving cars, but on any system that relies on cameras to navigate complex environments. Thanks for watching. Don't forget to like and subscribe to our channel.
See you next time.